introduction. So welcome to the second event of our cafe. Today we have Benno van den Berg, and he will give us a talk about effective count fibrations and simplicial sets. And so Benno, whenever you feel like, you can share your screen and start.
Okay. Okay, everyone can see the screen now, I think.
I can.
Okay, then I take it everyone can. So thank you very much for the invitation to speak at the Bohemian Cafe. So what I'm going to talk about is effective count fibrations in simplicial sets. And before I start with sort of the motivation, let me first of all mention a few make a few preliminary remarks. So the contents of this talk are all based on a preprint, which you can find on the archive. This is very much joint work with Erik Faber. And actually, Erik will also give a talk about this topic at the what I've called the Moravian Cafe. So that's the Masaryk University Algebra Seminar on March 11. So if people are interested in a different perspective, or then they can also attend that seminar. Okay, so basically the main question I am concerned with today is the following one. Basically, the question is, what is the correct constructive definition of a count fibration between simplicial sets? So in a way, that is a kind of mathematical question. I mean, I could call it a more conceptual question. And basically, the first thing I want to do is to motivate why we would be interested in answering this question, also from a sort of a logical perspective. And the answer is that the motivation comes from homotopy type theory. And so we'll start by saying something about why homotopy type theory would lead someone to ask this particular question. So there is this sort of logical motivation for it. At the same time, I would argue that what we do in our paper is a chapter in simplicial homotopy theory, basically done from a very sort of particular perspective, where we're very interested in rather than sort of very interested basically in doing all kinds of explicit constructions rather than sort of inexplicit arguments. And I think even for a classical homotopy theorist, I think it is interesting to see how that sort of works, how that pans out. So important for our motivation is that everything is constructive. All our arguments are effective. We do everything in a way which should have some computational meaning, or could be internalized inside its opos. But even if you're not at all interested in that aspect, I think there's still new mathematics in the paper. So sometimes constructivists try to redo parts of classical mathematics within a constructive framework, but what we're doing is a bit different in that sense. So basically the motivation, as I said, comes from homotopy type theory, and homotopy type theory is a sort of a development of type theory, Martin-Löf type theory in particular. So maybe I'll first say something about Martin-Löf's constructive type theory. So I think the motivation, Martin-Löf's motivation for formulating his type theory is a way of sort of making explicit his philosophy of mathematics, which was constructivist. So it is supposed to make really precise a kind of constructivist philosophy of mathematics. So there's a foundation for constructive mathematics. At the same time, he also points out that you could actually think of this as a functional programming language. And the reason for this is that, I mean, a constructive proof is in a way like an algorithm. There is everything done inside this type theory. It has a computational interpretation as well, and that can be exploited as a functional programming language, like in the style of Haskell. And it has also been implemented, so it is the basis of also proof assistance. So you can also use it to sort of verify mathematical proofs. And it has been implemented, so it has been at the basis of Agda, which is very close to Martin-Löw's intentions, or Lean, which also, which also uses Martin-Löw's dependence type theory at its basis. So this is sort of the important sort of aspects of Martin-Löw's type theory, and I think maybe it's good to say that so it is a formal system. You can also think of it as a formal system in which you derive statements like these, which basically mean that so the gamma here is a certain context, which is not so important. Then A is a certain term, and sigma is a type. And there are two readings always of this. So you can think of the type sigma as being a mathematical statement, a proposition, and then this little a is a proof of that proposition. At the same time, you can also think of the sigma as a kind of specification. So if you're looking for a constructive proof of a certain statement, in a sense, you're looking for an algorithm which has certain properties, which you could call specification. And then you can also read it as A is a computer program meeting this specification sigma. So there are these sort of two readings of these statements that you derive in type theory, and it is often called proofs as programs or propositions as types. And then some important properties of type theory are the following. So first of all, so these are the kinds of statements that you derive in type theory, and the question whether such a statement, I mean, assuming it has the right grammatical form, is derivable or not, is actually a decidable question. So this is kind of different from most foundations. I think if you think of like Zermelo-Fraenkel set theory, if you give me a formula in the language of set theory, you're not able to decide whether it is derivable or not. But in Martin-Löw type theory, that is actually the case. And I think this is an important design decision for the type theory, because so I think if you think about this proofs so if you think about this as a mathematical statement, you think about this as the proof of that statement, then I think basically what we're saying is the question whether a certain object is actually a proof of that statement or not is actually a decidable question. So we should be able, if you give me a statement and a purported proof of that statement, you should be able to check whether that is actually a proof or not. So in that sense, I think this sort of also philosophically motivated. At the same time, we think of these little a's as like algorithms which you can sort of evaluate or you can compute, and that is often based on a sort of a term rewriting system. So there's a norm, and which is normalizing, which means that if you start with just an expression A, you can normalize it, and the system proves that the original thing that you started with and the normalized form thing are actually the same definition. This has all kinds of consequences. In particular, there is the property called canonicity. So if you start with let's say if you start with a closed term of type natural numbers, if you normalize it, it actually becomes a numeral. So in that sense, every expression, like closed expression that you write in type theory, can actually be evaluated to a numeral. So can that, in that sense, be computed, calculated, evaluated. Yeah. So these are the important sort of properties of type theory, sort of guided Martin Love in setting up the system in the way he did that. Now, as a foundation for mathematics, I think people already sort of noticed that there are several drawbacks. So, especially if you think about how things are sort of done usually in mathematics. So it is, first of all, it is in a way an intentional system. So you cannot prove that two functions are the same if they give the same output on the same arguments, whereas standard mathematics is sort of resolutely extensional. There are also problems surrounding quotient types. So one thing that one does often in mathematics is when you have an equivalence relation on a set, you can quotient, and sort of the equality on this quotient sort of replaces the equivalence relation that you had on the original set. That is hard to sort of square with this whole sort of design of type theory. And then sometimes, so everything that you do in type theory is automatically sort of proof relevant. So these proof objects are carried along all the time. And sometimes that is just a nuisance and you want to get rid of it. So people have thought about bracketing, but I mean, okay, so these are sort of, I think, even, so these are well-known sort of difficulties in type theory. So I think the things that people found attractive about homotopy type theory when it sort of arrived on the scene was that it promised a kind of new perspective on these old problems, and in particular, maybe it could even be used to sort of solve them. So I mean, there's a lot to be said here, but I'm not going to do that today. So I think the slogan, or the sort of fun, if you want, is that we interpret types as homotopy types of spaces. And this is a kind of, so you can think of it that we interpret types as spaces, but we're not sort of interested in all the information within the space, but we're mainly interested in the points and the paths between those points, and the homotopies between those paths, and the homotopies between those homotopies. So in a sense, that's usually called the homotopy type of the space. And I think that's, so I think the idea is that by interpreting these types of these homotopy types, this suggested all kinds of new proof principles in type theory. So Blavatsky sort of formulated his univalence axiom. Other people, I think at the Oberwolfach meeting, arrived at the definition of higher inductive types. Right now, I don't think I want to dare attach names to this. I have to look this up. Anyway, but I mean, as a consequence of these principles, I mean, so Blavatsky showed univalence implies function nationality. You can get certain quotient types by certain high inductive types. High inductive types, a certain particular kind of high inductive types give you propositional truncation, which is a kind of bracketing. So it in a way, it provided a kind of unified perspective on these problems that people were already sort of dealing with in the type theoretic community. So I think that was, I think, one of the big attractions. One of the problems, however, is that, I mean, it's nice to have an interpretation of type theory as a certain kind of geometric structure, which suggested all these things that you wanted to have in any case, but at the same time, you can't just add those principles just like brute force to your type theory without without sort of destroying sort of all these nice computational properties like normalization and canonicity that I mentioned before. So I think that was I think is was one of the problems that people sort of had. And I think right now, I think the preferred solution to this is cubical type theory. So in that sense, so that is a formula, and sort of like an extension of modular type theory, in which you can actually interpret equivalence, and you can construct certain higher inductive types. And it has these sort of desirable computational properties that I mentioned before, like canonicity, homotopic. There's also a modified version of canonicity called homotopic canonicity. And a week ago, there was also a preprint posted on the archive claiming that it has a form of normalization. So in that sense, it is, and as a consequence in cubical type theory, we have these things like function extensionality, form of quotient types, and propositional truncation. So I think that is sort of in some sense where we are in type theory. And I think it is no exaggeration to say that all of this work strongly, sort of the crucial step, I think, for all of this is a particular definition due to Thierry Coquin of a uniform Kahn fibration in cubical sets. So it is which interprets the type dependencies so there's a kind of model construction in the background. So there's an interpretation in cubical sets. And the question is, which morphisms of cubical sets will interpret the type dependencies? And the answer is, well, Thierry Coquin gave this definition of a uniform Kahn fibration. And this, all these other sort of contributions also rely on that. So, I mean, I think a natural question, I think something I would definitely be very interested in is, could there be something similar for simplicial sets? So could there be something like simplicial type theory, which has similar properties? So,
Benno, can I interrupt you with a question right now, since this is kind of the philosophical part?
Yes, you can. You already have, I guess. Yeah.
No, here comes the question, though.
Okay.
Can you comment on why it is that the constructive approach using cubical sets seems to have so many better properties than the classical approach using classical simplicial sets? Maybe it's not the difference between cubes and simplices, but the difference between constructive and classical mathematics. But do you have or is there a trade-off? Have we also lost something? It's a philosophical question.
It's a philosophical question, yeah. Well, I think, I'm not sure I've ever have an answer sort of right away. I mean, in the sense, I think the question, of course, is that, I mean, one thing, of course, is that people, if you want to sort of implement things on a computer, there should be, I mean, it's not, I mean, it's important in a way. You're sort of automatically let all kinds of sort of questions of effectivity or constructivity. So in that sense, the question of what you can successfully implement on a computer and what you can sort of prove in a constructive matter theory are sort of very intimately related. So if the particular definition that Thierry Coquin used is something which, for example, works very well in a constructive matter theory, then it is a good indication also that it is the correct definition to use in your implementation. And of course, there are certain abstractions that people observed. So I mean, there's in particular the construction by Benno, and Parman, that which I think also was important also for the development here, is that so basically the Kahn complexes, if you use in simplicial sets, if you use the standard definitions, are not closed under exponentials in the constructive matter theory, which basically tells you that somehow there is something wrong, if you want. I mean, if you want to interpret, you want to have function types, and the natural thing to interpret in, let's say, in simplicial sets, and the natural way to do this is by using exponentials, the exponentials that exist in simplicial sets, and that somehow doesn't seem to work very well with the standard definition of a Kahn complex or a Kahn fibration. But if you were hoping for a more philosophical answer, I'm not sure I can give it sort of right away. Okay.
No, that's fine. Thanks for giving it a try.
Yeah, sure. So I think, but I think maybe it's good to mention that also, that I mean, so I think this was also the reason why people started switching to cubical sets. I think Jericho Kahn originally wanted to have a kind of constructive account which worked for simplicial sets. They observed, for example, this Benno-Kahn-Parman obstruction, and they did two things. They started adding these kind of what they call uniformity conditions, and they switched to cubical sets. And somehow the question remains like, so these uniformity conditions are maybe a good idea, but could you have done only one of those two things, like added uniformity conditions and stayed in simplicial sets? And that is still, that is what I'm trying to do today. And I think so I think there are several advantages, could be several advantages over the cubical approach. One is that people use all kinds of cubical sets. So there are many different variants of cubical sets around. Whereas there's only one version of simplicial sets, so we don't have to have a discussion about what do you mean by a simplicial set. One thing is also that the Kahn complexes in simplicial sets really interpret the homotopy types. So there's a discussion about in which variants of cubical sets, if we use the definition of Kahn complex proposed by Coquin, does it actually adequately capture the worlds of homotopy types, and that is sometimes just false and sometimes unknown. And so I think people worked on equivariant Kahn complexes, but I think that there's still a bit of uncertainty there, which would not exist for simplicial sets. And I think maybe the main argument is why maybe want to have a simplicial type theory is that if you want to connect to the work that happens in homotopy theory, simplicial techniques are way more present, pervasive in the area than cubical approaches. So if you want to sort of connect to that, then I think it is interesting to sort of look at simplicial approaches. So if we want to do something similar for simplicial sets, I think the starting point should be the correct constructive definition of a Kahn fibration in simplicial sets. And then I'm back to where I was in the introduction. Why are we interested in this particular question? Are there any other questions? Because from now on, I'm going to be more technical. Okay. All right. So, so what do we? So what is sort of the quick summary of what we do in our paper? What we do is we propose a definition of an effective confibration in simplicial sets, which has the following 4 properties. So basically, they're closed under pi. So let's say closed under push forward. So basically, that means that we can. So basically, the idea is that we want to interpret pi types in simplicial sets using the locally Cartesian closed structure of the category of simplicial sets. And if that means that if you want to use the right adjoint to the pullback, so we want to the pullback functor, and then if you give me basically a confibration and I apply this right adjoint to push forward along another confibration, I want to get another confibration back. That is important for interpreting a certain kind of constructive type theory, the pi types. Then another thing is that we want the definition of an effective confibration to be in a way correct, to make sure that it agrees with the classical notion of a confibration. So the standard definition that you find in textbooks on homotopy theory is that it has the right lifting property. There are maps in simplicial sets which have the right lifting property against Horn inclusions. So so I mentioned the Bateson compartment obstruction. So that's probably not a very good definition in a constructive setting. So, but still, if you would work in a classical matter theory, it should be equivalent to the standard definition. We don't really want to deviate from the classical theory in that way. So what we want is, what we will actually do is that our effective confibrations will have the right lifting property against Horn inclusions, but the converse is only true classically. So that means that if you have a map which has the right lifting property against Horn inclusions, then classically you can also equip it with the structure of an effective confibration. And then finally, so we make one step towards the construction of sort of universes. So that's another important type of constructor. So we can constructively obtain something called universal effective confiberations. And I think, so our claim is that, I mean, there have been different approaches. I mean, we're definitely not the first ones to think about this question of how shall we think about confiberations in simplicial sets in a constructive framework. For example, there is the work by Simon Henry, which was taken up also with Nicola Gambino and Schmilo and Christian Sattler. So there they only have sort of weaker pi types. And then there's also the work by, which I will probably come back to, by Gambino and Sattler, where they, I think, ran into trouble with the universal effective confiberations. So, so that's, so I think we can sort of do both these things. All right. So before I go on to talk about our definition, let me just sort of very quickly also just to get into the right sort of frame of mind, let us just think a bit about the classical definition. So the classical definition is phrased in terms of lifting properties. So a map P from Y to X is a configuration for any Horn and any sort of commutative square, like the one I've drawn. There is a filler which makes, so that's the dotted arrow here, which makes everything commute. So I think from a constructive point of view, I think the first question to ask is the following. So this sounds like a property. Right? So for every square of a certain type, there should exist something that has certain properties. But is that really a property, or should we really think of that as structure? So, like, I mean, a confibration is just a map of simplicial sets which comes together with an operation effective operation, which given such a square actually gives you a filler like this. And I think, yeah, I think from a constructive point of view, it is indeed a better idea to just have this as a structure. Oops. So that, yeah, so that it's not just a map of simplicial sets, but it's a map of simplicial sets together with an explicit choice of such a filler for each such lifting problem. Now, the next question to ask oneself is that, okay, so once you make this choice, that you have this choice of filler for each such problem, do these fillers have to satisfy some additional sort of compatibility conditions? So, right, can they be completely random, unrelated solutions to these lifting problems, or are there certain compatibility conditions that maybe you want to be satisfied, so that they, yeah, so the solutions are related in some way? And that is actually, I think, also what, yeah, so going back to the work of Thierry Coquin in cubical sets, what basically his uniform configurations also did, they said, no, there should be certain connections between these, the sort of compatibility conditions satisfied between between the solutions to these lifting problems. So they cannot be completely unrelated. There are certain compatibility conditions should be satisfied. And what we want to do is, what we're doing is in the same sort of vein. So yes, we can't just sort of choose our solutions sort of in a completely unrelated way. There are certain compatibility or uniformity conditions that should be satisfied. But then the question is, which ones? I mean, please identify the correct compatibility conditions, and that's really what where we make a certain sort of suggestion, suggest a certain solution of what that should be. Now, to phrase, so I think in our paper we actually we give several different definitions of what these effective configurations that we're interested in actually are, could be. And actually a large part of the paper is also sort of just basically showing that the different definitions that we have are actually equivalent. So what I want to present for the experts in the audience is my favorite definition of these effective configurations, which I think is the most sort of pretty. But to phrase these, to state these, this definition, I will use the language of algebraic refactorization systems, which are, so refactorization systems are well known in homotopy theory, but there is a kind of explicit variant of them, which are called algebraic refactorization systems, and we use that sort of setup quite extensively in our paper. So I think I can't sort of go into give a sort of huge sort of like a quick introduction to this theory, but let me just mention very quickly what it is basically about. So in a refactorization system, you have a factorization of your map. So what we are, so the first ingredient is that we want to have a functorial factorization, which you can of every map in your category. So and that is can state very compactly as a section of the composition functor. So the composition functor. So that's what's called a functorial factorization on your category. So that basically means that for every map F, you actually get two maps, L of F and R of F, like these over here, and their composition is the original map F. So once you have this, you can define, you automatically get two endofunctors on C arrow, on the arrow category on C, and that's just L, and that's R. But you also come automatically, you also get automatically like a pointing and a co-pointing. So there's a certain natural transformation from L to the identity, and from the identity to R, and those are basically given by these squares over here. So the idea behind these algebraic refactorization systems, going back to Gomez and Tolan, and is that what we actually do is, so we have two AND functors, and we have in a sense like a unit and a co-unit. So let's also demand the existence of a multiplication and a co-multiplication, so that these things are monads and co-monads on the arrow category. And then Richard-Garner suggested to add a distributive law for the co-monads over the monads, and I think that's a good idea, and we follow him in that idea. And then the idea is that, yeah, so once you have such an algebraic refactorization system, you get two classes of maps. You get left maps, which are the co-algebras for the co-monads, and you get the right maps, which are the algebras for the monads. And you can prove that both are closed under composition, and that the left maps have the left listing property against the right maps, and that actually have an explicit choice for these fiddles. In fact, the two classes, so the left maps and the right maps, determine each other sort of completely. In a sense, for that actually you use the distributive law quite heavily. So in all of this, if you want to know more about these things, I mean, there are some papers by Emily Weil which are quite kind of nice, and then there's also this kind of very comprehensive treatment in this paper by Berg and Garner. So I mean, and then yeah, so I mean, one important thing is that these left and right maps are not automatically closed in the retracts like they are in normal refactorization systems. But you can take the retracts closures, and then you get an ordinary refactorization system. So every algebraic refactorization system has an underlying normal refactorization system in that sense, in that way. Yeah, so as I said, I mean, to define our effective configurations, we rely on two, we rely on the existence of two algebraic refactorization systems on simplicial sets. One is the trivial configuration, cofibration trivial configuration refactorization system, which we have to sort of adapt a bit in the constructive setting that we work with. So our notion of a cofibration is that a map, I mean, usually in the classical matter theory, it is just a monomorphism of simplicial sets. But for us, it is a monomorphism of simplicial sets which satisfies a certain decidability condition. So what we want is that you can decide for the element, and so if you have a map from Y to X, you can decide for the elements in the simplicial set X whether or not they actually came from something in Y. So in the sense, the question whether or not you are in the image is actually is decidable, and yeah, then you also want, if it is in the image, you want to be able to construct the element in a pre-image that it came from. So these maps, you could call these things like effective cofibrations if you want. These effective cofibrations are actually the left class in an algebraic refactorization system on the category of simplicial sets. Okay. If you're a classical mathematician, you can just think monomorphism. Then the other algebraic refactorization system comes from a simplicial Moore path functor. So in an earlier paper together with Richard Garner, we defined a certain endo functor on the category of simplicial sets, which we call M, for Moore paths. And what happens is that every simplicial set, it becomes the object of objects of a certain internal category in simplicial sets. So there is, I don't know, there is a kind of composition operation, there's a source and a target, and there is like a reflexivity, like an identity arrow operation, and you can sort of prove that it satisfies the axioms of an internal category. But what we think of, is we think of the elements of M of X as in a way of sort of more paths in X. So more paths is like, so the intuition comes a bit from topological space. It's where a more path in the topological space is a path in the topological space, but it need not have length 1. So it doesn't, but it can have arbitrary length, some real number. But then by doing this, paths can be composed like in a way which is strictly associative and strictly uniform. And something similar happens here as well. And in addition, there is this thing called a contraction. So if you give me a path, let's say from A to B, I can sort of, some people call it the vacuum cleaner principle. I can sort of contract it onto one of its endpoints, let's say onto B. And then, so then I get a path of paths going from the original path back to the path which is sort of like of length 0 at its endpoint. And in addition, M is actually also an endofunctor, and it preserves, and all these maps like R, S, and T are actually natural transformations. So actually, it means that there is a kind of congruence. I mean, you could define a notion like M homotopy on the category of simplicial sets. So basically, so you could say that two maps from X to Y are F and G are M homotopic if there's a certain map to M of Y, which sort of says that they're the same via Moorpath.
Sorry, may I ask one quick question? So this construction you can more or less have it in every category with a cylinder object, or you need precisely simplicial sets to build this functor M?
So okay, so I mean, from what I've described, you could do this in every category which has a sort of cylinder object together with something like connections. However, which simplicial set has based on the interval in simplicial set. However, that's not what we do. So that's not how the simplicial Moorpath functor actually works. So it's more complicated. If people are interested, maybe in the Q&A session, I can say more about how the construction of this M. For now, I just want to use it as a black box, but I do want to make the following remark, is that this notion of M homotopy that we get is in a way that, I mean, maybe we haven't stressed this enough also in the paper, but it actually is the correct notion of homotopy. So, homotopic maps in the usual sense with respect to the, let's say, the interval are also M homotopic. And if you have and the converse also as well, if you actually look at maps between count complexes. So in that sense, I would say it's actually M homotopy is in a way the correct notion of homotopy. So it's not something completely weird. And then basically, as soon as you have a notion of M, if you have such a Moorpath function, you can actually make quite kind of, using the sort of the usual sort of path fibration factorization, you can sort of factor it like this, and you can check that all the structure necessary for an algebraic weak factorization system is actually present. So that gives you, so this gives you the functorial factorization, and then you can check all the other structure that you need is also there. So then you get two classes of maps, the left maps and the right maps with respect to this more functor. So then the right maps we call naive fibrations, so we call them naive fibrations because every count vibration is also a naive vibration, but the converse is not true. In fact, every simplicial set is naively vibrant in this sense. So that's a bit strange, but what we mainly use is the left maps that you have. So these are the algebras for the co-algebras for the co-mole maps that we were saying here. So let me see. So what are the algebras, the co-algebras for this co-monad? Let me draw a picture because I think that's actually helpful. So they are basically monomorphisms in simplicial sets. So there's a Y sitting. I mean, I think of this as sort of like some sort of deformation retract. So there's a Y sitting inside an X, and but every element in X is sort of connected. Yeah, so for every element in X, there is a path to a certain element in Y, which is, and then we choose the identity path, or more path on all the objects in Y. And then there is this particular condition that needs to be satisfied. And actually, this is kind of a natural thing, I think. Basically, it tells you that, so if you have this point here, then you have a certain path which goes to Y. But if you would look at a point which is sort of halfway through this path, then also that point should be connected. So you choose for that point a certain path which goes to Y, and the choice that you have to make is basically the same path which actually just started at that point. Understand what I mean? So that is this sort of equation over here, where this P should actually be N. Anyway. So these are deformation retracts, which are in a sense stronger than usual. So that's why we call them hyperdeformation retracts. Because of this condition, this extra condition that we have. Now, an important example of such hyperdeformation retracts are the phase maps. So so a map from delta n included as a phase in delta n plus 1. This is actually an example of a hyperdeformation retract. And the one thing that the hyperdeformation retract has is the retraction, and then we choose one of the degeneracy maps. So such a pair of a phase and a degeneracy map, which when composed are the identity, is an important example of a hyperdeformation retract in our sense. Okay, and then we prove several things about these hyperdeformation retracts. An important thing is that these hyperdeformation retracts give you a certain growth-induced vibration. So what it means is where we use a domain function. So suppose you have a certain hyperdeformation retract, I don't know, I from A to B, and you want to and you are given maybe a certain map from A prime to A, and you want to pull this hyperdeformation retract back along this map. And you can do that because, well, actually there is a retraction which goes back to A again, and then here again is this map from A prime to A, and then you can sort of say two pullbacks, so you get something like this. And then you can check that this thing, so if this thing over here was an hyperdeformation retract, and this one over here was as well. So this is an important construction that you can do on hyperdeformation retracts. And also you can show that the category of hyperdeformation retracts. So there's a category because there's the other category of co-algebras for co-monad this is pullbacks, and the pullback of a Cartesian morphism is again Cartesian. Okay. Okay, maybe I wanted to make this picture some other way. So we're almost there. I can almost sort of state our definition of an effective configuration, but for that first I need another definition, and that's that of a mold square. So what we call a mold square is, in a way, it's very, can we define it very simply? It is a morphism of HDRs, which is Cartesian over a cofibration. So basically what happens is that, okay, so suppose I give you a certain hyperdeformation retract over here, and I give you a certain cofibration, from, let's say, from A0 to A1, and then I just pull this HDR back along this cofibration. So what happens is that I have this retract here, and then I can take this double pullback here. And then this thing over here would actually then be a mold square. So and then it is, yeah, so then it is a morphism of HDRs from this from top to bottom, and this thing over here is a cofibration. So that's what a mold square is. Then funny geometric properties that you can prove for these mold squares. So they have, and we basically have three kinds of properties. So mold squares can be composed both horizontally and vertically. So if this is a mold square, maybe like this. Okay, so these are the HDRs, and here I have another mold square. So then I can compose them, and I get another mold square. They can also be composed vertically, like this. And there is also a kind of base change property that they have. So if maybe I have a mold square here at the back, and then here at the bottom I only have let's say a morphism of HDRs, I can pull this mold square back along this HDR at the bottom, and what I get is that a front face, which is again a mold square. So if the category, I mean, actually there's a kind of triple category in which these mold squares live. Okay, so now I can state our definition of an effective configuration, and in a way what I want to say is that these effective configurations are maps which have the right lifting property against the mold squares. And I mean by that I mean the following. So suppose I have a picture which looks like this, I mean like a solid picture. So suppose here I have my map P, which I want to be this effective configuration. Then I have I think you can see my mouse. So I have a picture which looks like this. So over here I have my mold square, and I also have this map from C to Y. And what I want to be able to find is this dotted arrow, this map from D to Y, which makes everything from this. So that is what I want. And now in a way, the natural compact, so that structure should be there. And then the natural the compatibility conditions that these lifts, so these dotted arrows, should satisfy, actually, in a way, basically just are supposed to reflect all of the structure that these mold squares have. So for instance, so I don't know, I mean, I think they're kind of very natural. So suppose I have a mold square like this, a mold square like this, and here I have my configuration. I think the configuration, and suppose I also have a map. I don't know, maybe I can draw it like from here to there. And now I want to arrive at a map from here to there. And there are two things I can do. I can sort of compose these two mold squares and then push this arrow forward sort of to an arrow here. Or I can do it in two steps. I can first use that this thing here is a mold square and then push this arrow over here forwards to a map over here. And then I have a similar lifting problem here. And then I can again obtain a map like this by pushing this one over here forward. You understand what I mean? And then the natural condition is that these two maps that I get from here to there, they should actually coincide. And yeah, so I think, I don't know, there is, I think similar for this vertical composition of mold squares, there's a very natural compatibility condition again, and also with this base change condition, I think there's a very natural compatibility condition that these things should satisfy. So for instance, if you have a problem like this, you can either sort of first compose these two mold squares and get a map over here in one go, or you can look at this composition going first here and then over there. So then you can also get a map here. Then you can push this one forward, I don't know, and then this map together with this map also give you another solution over here. I think you will be able to figure it out if you sit down. So what I think what I like about this, I mean, we've set up this sort of maybe alien technology of these mold squares, but once you have set this up, I think the compatibility conditions on these lifts are a very natural reflection of this kind of geometric structure that these mold squares have, reflecting horizontal composition, vertical composition, and its base change condition. So that's what I like especially about this particular definition of these effective Kahn fibrations. Yeah, so let me just remind you that what we've shown is that, so we can construct pi types reflecting the locally Cartesian flow structure based on this definition. We can show that these effective Kahn fibrations have the right lifting property with respect to Horn inclusions. The converse is only true classically, and we can construct these universal effective Kahn fibrations. Let me just also do this slide because I think this is just sort of fun. Maybe before I do that, let me just mention, because I think this kind of lifting problem that I have over here, it can actually in a way be stated more simply, because if I have a solid diagram like what I've written here, that I could also just as well as sort of abbreviate it in the following sort of more familiar looking lifting problem. So I can take the push out of these two maps over here. So then I get a map from B push out over A, C. And then this induces a certain map to D by the universal property of the push out. And then this sort of solid data is the same thing as a square like this. And this dotted arrow is the same information as just a solution here. So this lifting problem against the square is the same lifting problem against sort of this inscribed map from the push out down to D. Why haven't I stated it like this? Well, because if you do that, then these naturality conditions, the compatibility conditions, look very strange and unappetizing. But if you state it in terms of lifts against mold squares, they look kind of nice and natural. That's basically the point. But I mean, it's important to realize that this lifting property against this mold square is just the same problem as the lifting property against this particular sort of inscribed map. Okay. Having said that, why is it the case that effective Kahn fibrations have the right lifting property with respect to horn inclusions? Well, I mentioned that this is a particular HDR phase map together with sort of one of the degeneracy maps, which is a retraction of that. And let's just imagine that I pull this back along this whole situation back along the face of this end simplex. Okay, then I take this sort of double pullback, and then by definition, this will be a certain mold square. So what does it mean to have the right lifting property against this mold square? Well, it's the same problem as having the right lifting property against this inscribed map from the push-out, but that's just a horn, as you can sort of, as you might check. So for that reason, effective configurations have the right lifting property with respect to horn inclusions. Yes, and in fact, one thing we show in the paper is that the lifts against these sort of, so we call mold squares which look like this, pattern over here, we call these horn squares. And one thing you can actually show is that the lifts against the horn squares determine all the other lifts against all the other mold squares. So in a sense, it looks like we've sort of gone very far away from the traditional horns, but in a way we sort of recovered it. We recovered the horns in a rather sort of, well, it takes a lot of effort to actually prove this, but the horns are actually in a way still there. And all right, let me wrap up. What I think we can claim is that we can actually construct a kind of, based on this definition of an effective configuration, we can construct a kind of model structure on simplicial sets, provided we restrict to those objects which are effectively calm. We have these type constructors, but that's not where we want to go. I mean, we want to go further. We want to actually have a full model structure on the entire category of simplicial sets. We want to be able to interpret other kinds of type constructors as well, in particular univalent universes. So, so I said we have universal configurations, but we don't have universes, and then we don't know whether they're univalent. So in fact, right now we're looking at the univalent axiom. We're trying to copy in a way just what happens in cubical sets. In fact, that's very often the strategy that we follow. We just look at what has been done in the cubical world or cubical type theory, and we just try to sort of mimic that as good as we can in the simplicial world. So we haven't shown that universes are effectively calm, which is also important. We haven't shown, we haven't shown that there is this model structure. So there's still a lot of work to be done, but at least I hope that with this definition of an effective configuration, we have made an important step towards all of these things. So let me thank you for your attention.
So thank you, Benno. People are applauding, but of course, we cannot hear it. So thank you very much for your talk. So and now we have the question time. So if someone wants to ask a question, that's a good moment to unmute yourself and just ask.
I have a tangential question. So
okay.
If you assume classical logic, then you get this converse, that right lifting with respect to horn inclusions implies effective configuration. Can we go the other way? Assume this characterization of effective configurations. Can one, say, by specializing it to some particular cases, derive some either law of the middle or some weaker classical logical principle?
That's a fun question. I haven't thought about that at all. It's a kind of reverse mathematics. No, I haven't thought about that. That's nice. thanks for the question. Yeah. Someone is saying something in chat. Thank you, Nicola, for your question.
Yeah, goodbye, Nicola. And of course, if someone else wants to ask something.
A question.
Oh, sorry. Go on, Stephen.
I have a question. One motivation for doing a kind of constructive version of simplicial sets would be that you're going to take simplicial objects in say a sheaf topos or something like that.
Yeah.
And you're going to make some simplicial sheaves, and then you put a model structure on the simplicial sheaves. If you do everything constructively, it should work in that more general setting. So now, of course, we already know how to make a model structure on simplicial sheaves using methods that Andre Joyal has developed. How does your construction, if you interpret it in that setting, compare to Andre's? Or maybe more generally, does your construction work in simplicial sheaves?
Yeah, no, okay, so first of all, it's a good point. I mean, another sort of motivation for this, I mean, it's not what's driving us at the moment, that another motivation for this could definitely be that you want to do sort of like simplicial homotopy theory inside that category. So yeah, so again, if the question is how does it compare to what Joyal has done, the answer is again, I have no idea. Yeah, it should also be on the long list of things to have a look at.
Okay.
Yeah.
That's okay. I didn't mean to put you on the spot.
No.
I thought you might have thought about, I mean, if you want to do a kind of constructive mathematics, as you know, a good way to do it is just to try to do regular mathematics in the sheaf topos, because that forces you to be constructive. And if you're constructive, it'll work. So for example, your definition of a cofibration that you gave us, that used some kind of, I don't know, meta intuition as if we can decide, blah, 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 right? But one would like to give a more mathematical definition.
Yeah.
I presume that you have one that makes sense maybe in a sheaf topos or something like that.
Yeah, sure. So it means, so it means something like being sort of point-wise complemented in of sub-objects.
Exactly.
Yeah.
Exactly.
No, that's right. Yeah. So I mean, yeah.
Okay.
So yeah. So I think this yeah.
Okay.
Yeah.
There was something at the end of your talk. You said it's a problem to extend it to the full category of simplicial sets. Maybe I've misunderstood something, but I was always thought that you were that.
Yeah, no, that's.
The third item here.
Yeah.
Because I thought you define an algebraic weak factorization system within simplicial sets, but so what do you mean here?
Well, actually, okay. So, I mean, what I haven't claimed so far, for instance, is that these effective confibrations are the right class in an algebraic weak factorization system. They are in a classical meta theory. So I think I have So the problem is that uses a version of the small object argument, which seems to be quite sort of classical. So, but I'm pretty certain that that could be made constructive as well, but we haven't done that. So, and I think, yeah, so I think the strategy that we have in mind for proving that there is some sort of constructive model structure is basically the strategy that you can also find in Christian's Sattler's paper on the equivalence extension property, where basically what he uses is basically I think my idea is that once you show driven items 1 and 2 on this list, and you also prove this in a constructive matter theory, the right version of this sort of small object argument, which will give you that these effective confirmations are the right class in algebraic refactorization system, you have basically shown that you are that you have an algebraic model structure in some sense. Yeah.
So in a sense, you have defined what effective version of Kahn fibrations is, but it doesn't quite form a model structure, not even a natural or algebraic one.
No, I think there are. No, I think, well, I mean, there are several steps that are missing at the moment. I hope to be able to fill them in at some point. One question also is, what is an algebraic model structure? So Emily Real has a definition, but I think, so for example, I think people have been looking also at modifications of that. So, but I hope that there is one good definition possible that which these things would satisfy. But yeah, we are not there yet. And maybe one thing to add is that one thing which we are, so one thing that we don't expect will hold constructively is that these effective confirmations are closed on the retracts. And it's also not required in an algebraic refactorization that the system that the right maps are closed on the retract. And also, I think, yeah, so we're hoping also that, for example, some of the construction of the like the proof of univalence axiom and prime theory of the universe don't really require these maps to be closed on the retracts.
I mean, another thing which might be interesting to see explained is where precisely do you avoid this Betzem-Coquin paradox? Because they essentially showed we constructed a Kripke models where the Kahn guys are not closed under exponentiation. So, well, but so the difference is that they have a different definition of what the Kahn vibration is, right?
I think, yeah, so I wouldn't be able to point to sort of like a exact point in our paper where we work around this issue, but I think the idea is that these basically the uniformity conditions take care of this.
Okay. I see.
So I think that's what happens in cubical sets as well. I mean, as explained in this paper by Gambino and Stapler on the spontaneous property, they also explained that by making similar uniform, if you impose uniformity conditions, then you can also work around this ECP obstruction, also in simplicial sets.
I see.
So you basically, the problem arises because you need these kind of lifting problems to satisfy certain compatibility conditions, which are not automatically satisfied if you work constructively, but in a classical setting, you can always choose your lifts in such a way that these are actually satisfied. I think that's the point. Yeah.
So they just consider the different notion, I mean, different constructively, which classically is equivalent to the usual thing. I mean, so in both cases, if you work classical, it's fibrations, but it's different definitions. And their definition was more literally the same as in the classical case. Yours isn't.
I mean, but I think there's also a kind of philosophical difference, like whether it is a property or structure, but also try to sort of to explain sort of midway through the talk is that I mean, so as soon as you, so if it's just, so for us, it should be structure. And then the question is, so I mean, it is only when you sort of think of confirmation structure that the question like, should these lifts also satisfy certain compatibility conditions even make sense? Otherwise, I mean,
that's right.
Yeah. And people in classical in the standard sort of classical developments that they formulate things as properties. So and that means they don't need to worry. They can always if they see a solution to a lifting problem, then they can assume it is their preferred solution. Whereas here that is not the case.
So you mean that Betzem and Coquin simply showed that if you define Kahn vibration as usual without naturality, then this is not closed under exponents. Okay, now that answers it quite clearly. I see.
Yeah.
Thanks. Well.
So we have a question in the chat, but Tom, if you want, you can just speak.
Okay, thanks. If it's my turn. So it's probably very naive. I heard that the very definition of simplicial sets was problematic in constructive maths. Because, for example, you can't even test whether a given element is degenerate or not. So you don't seem to run into these kind of difficulties. Is it that you use another definition, or is it just because you're not going into each simplicial set?
No, so I mean, so also so I guess, so I think that is okay. So also, it's true. I think constructively, the question whether a simplex is degenerate or not is not decidable, and I think that was So I think we basically it doesn't play such a prominent role, this issue in the way we work. So we seem to sort of work around this issue in some way. It plays a very prominent role in the, for example, in the work around like Henri's work and also Nicola, Schmilo, and Sattler. And the reason for them is that so that they want to, for example, use the standard definition like of a trivial Kahn vibration, where these things are just sort of cofibrantly generated by the boundary maps. And if you take that standard definition, then you can't prove that every simplicial set is cofibrant. Because the cofibrant objects would be just those objects for which the question whether or not a simplex is degenerate or not is decidable. And the standard development of simplicial homotopy theory actually kind of implicitly uses quite often that the fact that every object is cofibrant. For us, this problem does not appear because we don't use that definition of cofibration and a trivial vibration. In fact, yeah, in our world, every object is cofibrant, and yeah, that's just yeah, and so in their definition of a cofibration, they would add an extra condition like, and for those elements which are not in the image, the question whether or not it is degenerate or not should be decidable. So they have added an extra decidability condition here, which we don't have. And I think it is kind of attractive to have every object cofibrant. Yeah, so I'm hoping also for that reason that we can make this work.
Okay, thank you.
Yeah, sure.
I'll ask one more question. Benno, are the cofibrations in your setup closed under pullbacks?
Yes.
Is there a universal cofibration, a cofibration?
Yeah. So so the cofibrations from a dominance.
Okay.
So
that's the question.
Yeah. So there's a universal cofibration. In fact,
So you could use I don't know if you've seen the way I have done things using the dominance, and then you make the trivial fibrations be the algebras with respect to that polynomial functor given by the universal cofibration. And then you get at least one of the setups is an algebraic weak factorization system. And that's completely constructive using the cofibration and the trivial fibration.
Yes.
Do you have that same setup?
Yeah. Yeah, that's also what we do.
That's half the battle.
Yeah. So in fact, I still like to think that we are somehow still also very close to sort of the Orton-Pitt world, where basically lots of things can be developed axiomatically on the basis of like having a dominance and having like an interval object. The only thing is we don't have an interval object, we have a more path functor. So if you look in our paper, it sort of consists of two parts, and the first part is like a purely sort of axiomatic, where we do this the closure on the pi types, which is done sort of purely axiomatically on the basis of basically a dominance and a more path functor satisfying certain properties. So it so that is sort of very much inspired also by Orton and Pitt. And I think it's kind of very helpful to think about it that way.
I have a question about maybe this is asking about too much speculation, but in this hypothetical algebraic model structure, do you have a candidate for the weak equivalences? Is that something that's extra structure as well? Or if so, do you have any idea what that might be? It seems quite hard, especially if you have arbitrary simplicial sets to describe what.
Yeah. So our idea would be to use the Sattler approach for constructing the model structure, where the weak equivalences are defined in a very indirect way.
So something like things that factor as a blank followed by a blank.
Yeah, indeed.
Okay.
So that gives you very little understanding, I think, of what they are. Of course, between fibrant objects, they're basically the homotopy equivalences, so that's a lot better. And I think indeed, so when I mentioned earlier, like there are different definitions of an algebraic model structure around, I think one thing indeed where they differ is whether or not you also want to have the weak equivalences be like a property or a structure, and what kind of structure should that be? So I think there is I don't know exactly anymore what the situation is, but But that is, I think, where some of the notions differ a bit. These people have tried to modify Remediable's definition because taking into account
Okay, so I'm sorry to say that I'm very happy to see that everybody is very active in the audience, but I have to stop the question time now. So we thank the speaker for the talk for the last time, and I think it's evident that the audience liked the talk because the audience has been very active. So thank you very much, Benno. And I shall remind you that next week we will have Joko van Hannen with strategic balance of gains in logic. And let me thank you for joining today and hopefully see you next week, I would say.
Yeah, thank you everyone for being here.
Thank you, Benno, for coming today.